Section 2.2 kind of gets the ball rolling with the graphs because there's all the histogram stuff in there. But Section 2.3 brings in all kinds of other graphs, and including ways that you can do them badly, which is what the deceive part is going to be about. But there are a bunch of other options besides histograms, even though I would say that histograms are going to be by far the most common kind of graph that you would ever see. So there are other options for quantitative data, and then you have some options for categorical data. So a dot plot is another option for quantitative data, where each value that you've got in your data set would correspond to a dot. That's supposed to be the idea here. And then if you get repeated values, then they get stacked on top of each other. So like if you look at this, it looks like there's just one value that's 70, but it looks like there are three 80s because they're stacked on top of each other like that. And that's basically the idea. And you can figure out things like shape if you have a dot plot, although maybe not too well from this one, because if you look at this, it looks like the dot plot's pretty low to the ground generally. So dot plots tend to be a little more effective with a data set that's a little bigger than this, because then the shape becomes a little easier to figure out. But it still kind of works like a histogram, except that you have a dot for every value instead of having classes where then you just know how many values are in each class. The next option is a stem and leaf plot, also known as a stem plot. There, it's another one where every data point is visible, and not only is every data point visible, in a lot of cases you could recreate the entire data set if you didn't have it. Like if you had just this stem and leaf plot right here, you could recreate like an Excel file with the entire data set in it. Because with IQ scores, they're 2 digits, so the things that you have in here aren't rounded off or anything. And if you see how this is set up, with the IQ scores, it's basically that whatever digit is in the ones place is the leaf. So I guess this vertical line here is kind of dividing where the stems are and where the leaves are. So the right side is the leaves, and then the left side over here is the stems. So like this 0, it's in the row where the stem is 5, and basically what we've got here is that these leaf values are the digits that are in the ones place of the IQ scores, and then whatever's on the left side is everything else. So like the tens place here, and I guess the tens and hundreds places down here for these ones that turn out to be 3 digits long. But you could look at these and go, okay, the first one's a 50, then there's a 56, then there's a 70, 72, 73. Down here, this big one's a 141. So you could recreate the entire data set. And that's great when you can do that, but sometimes you got to round off the leaf because you do need this graph to actually be accessible. So then with something like the state areas, I had to do a few things to get this to look reasonable. So what are the differences? I already went ahead and wrote these in. So in the stem and leaf plot here for the state areas, because just think about what we had with this. So this is from section 2.1 in those notes where the actual state areas are. This big one is Alaska. It's about 570,000, right? That's what that number actually is. So I set it up this way because if I didn't go that far with cutting it off for the stem, this would be so long that it would be hard to read. Even if I went 1 digit less far, I guess, and I said, instead of just what's in the 100,000s place, we're going to use what's there and what's in the 10,000s place, then I'd have to go all the way down to 57, and I mean, that's going to be at least 58 lines long. But that's not really accessible. It's way too long. So there's that. And I had to round off because the leaf can only be 1 digit. So I had to round that. So a couple of things. So here I've got the stem showing the digit in the 100,000s place. And with the IQ, it was the digit in the tens place, right? Like that's what that 5 means right there. Then the leaf here is the digit in the 10,000s place, rather. So like that's what that 7 is, or the 6, or all these things up here. And then with IQ, it's whatever's just in the ones place. The other thing that I had to do, other than I guess the fact that I rounded off, because that had to be 1 digit, not 5. Each individual stem value is in 2 rows. And the reason I did that is because of the first one. Where the stem is 0, if I didn't do this, that first row would be really, really long. So I basically broke them in half, where the first row is 0 through 4 leaves, and then 5 through 9. And you can tell, I guess, with those first couple, that that's what's going on, especially with that first one, since almost every leaf is in there, every possible one. But yeah, if not for doing that, you'd end up with something that's kind of awkward looking, where one of those rows is extremely long, and then the other ones are all really short. And you might be able to see what the problem would be with a stem and leaf plot at this point, which is that if every value that's in your data set gets its own leaf, what if your data set's huge? Then your stem and leaf plot might end up kind of huge and cumbersome. And that's the thing that we don't really want, right? We want something that'll be easy to read and easy to interpret. So the nice thing is that a lot of times every value in the data set can be recovered, because you could do it with the IQ scores, right? Maybe not here. I guess here with the state areas, you'd get rounded off values. So you'd get an idea of what the original data set would be like, but you wouldn't get the exact thing. But you could do it with the IQ scores, but you can't do that with a histogram. Right? With a histogram, all you'd know was, okay, this class had 11 values in it or something. So you wouldn't know what the actual numbers were. But you can recover that with the stem and leaf plot, and you can usually figure out shape. And the way that you do the shape, if I go up here to this one, basically it's you turn the stem and leaf plot mentally, I guess. So like you kind of rotate it so the stem is on the bottom. Because think about the way that a histogram is set up. Like on the x-axis, as you go left to right, the values get bigger, right? I mean, that's the way a number line works too. And that's essentially what you want with the stem. So you just turn it on its side. So like 0, 1, 2, 3, 4, 5 is going left to right. And then the way that you would look at the shape as far as like, is it approximately symmetric, or is it left skewed, or is it right skewed? Those things work the same way as they would with a histogram. So here you'd be thinking, okay, if I turn this sideways, there's the peak. The left tail doesn't stretch out too far, but then we've got a right tail. Then we've got a huge gap, and there's an outlier. But still, we're going to have a longer right tail than left tail, so it's going to be right skewed. And that's what we got when we had a histogram of this exact data. So that's generally the way that you would work it, and we're getting the thing that we're supposed to. So certainly that's a good sign. So you can usually figure out the shape, I guess, unless you've got your stem and leaves calibrated weird, then maybe it doesn't work. But, like how here we had to make a couple of adjustments, like put each stem value in 2 rows for one thing. That helped, and we can certainly figure out the shape from here. The drawback is that the stem and leaf plot does not work well for large data sets, and it's the very same thing that makes this work causes this problem. It's that every value has its own digit, right? Every value that was in your data set. So here, this one's got 634 values, and the row that's going all the way across, I actually had to cut that off. It keeps going. And that becomes a problem, because then, like, that's kind of an awkward looking thing, hard to interpret, right? Too wide, realistically. Even though I used another program to make this thing, I basically had it lined up to where it's aligned with the margins in this document. And this is maybe 4-point font. Like, that font size is really small. So with a big data set, this doesn't work so well. But if you have a data set that's relatively small, like 50 or 60 or something, then the stem and leaf plot's going to do a great job. But here, when it's 634, it's really not going to work so well. And a lot of people view the stem and leaf plot as sort of a quick and dirty version of a histogram, where a lot of times you'd see like a stem and leaf plot just kind of scratched out by hand. And there, yeah, if you're going to do it by hand, you don't want to have a huge data set because it's going to take forever, right? And you probably don't want that. But generally, it's good for small data sets, not so good for big ones. I think that's a reasonable way of looking at it. And then if you use a dot plot for the same data, notice what happens here. And this, I did use StatCrunch to do it. But the one value corresponding to one dot idea eventually gets thrown out by StatCrunch once that picture becomes too cumbersome looking. So at some point, it would ramp up from one value per dot to 2 values per dot, and then it would take the next step and go up to 3. And here you can actually kind of get a shape out of this, right? Where you go, well, here's the peak clearly. And so you have this long right tail, you got a short left tail. Looks like we got an outlier because we got this huge gap in here. And that is an awfully high fare. So hopefully that wasn't just due to dynamic pricing or something. That hopefully that was one where they just had to go really far. Because that looks enormous, right? It's almost 120, and that's maybe 70, the next highest one. But yeah, here you look at this thing, and how I mentioned earlier with the dot plot, you can basically read it like you would for a histogram to figure out shape. I mean, here you can really tell, right? Because you still look for the highest point, you go, okay, that's the peak, and then that's the long right tail, short left tail. This is right skewed. So yeah, works pretty much the same way. All right, the other options, let's see, a bar graph. So this is for categorical data, really. Where then, and I guess this kind of goes back to 2.1, where we had this table, where there was the idea of even if you have categorical data, you can still make a frequency table, you can still make a relative frequency table. You just have individual values instead of classes. So I've actually got this set up in a specific order that goes along really well with another graph that shows up here. But for a bar graph, generally this is kind of the conventional order too, where you have the frequencies going down, right? So they're all starting at the big one and decreasing, except that you have other, just put that on the end no matter how tall it is. But other than that, like if you look at a bar graph, it looks like a histogram to a large extent. It's just that the bars don't touch, and the idea of shape doesn't make any sense because there's no order down here. Right, these values are just different categories. There's no greater than or less than idea, so you don't really have shape. But other than that, I mean, it's basically what you would anticipate. And if you wanted a relative frequency one, you would use these percents instead of the counts, and you would get a graph that looked exactly the same. It's just that the y-axis would be calibrated differently. Next, a multiple bar graph. So then if you wanted comparisons, so like this would be good if you had maybe a stratified random sample, and then it was something that was categorical. Then that would make sense. I guess the big thing is that then you have for each category, because here really your different categories are the different years. So if you're looking at this and thinking, wait a minute, this is about income, that's quantitative. Income is quantitative, but that actually isn't really the thing that we're treating like the variable. We're kind of treating year like it's the variable here. So that has a natural progression, how you would write out the order of those different categories. But then what we've got as far as like how do you make the graph, you still have the gaps like in between like 2000 and 2010 or between 1990 and 2000. But then when you have your two groups that you're comparing, for each individual year, those two bars are right on top of each other, right? They're touching each other. So that's how you would set that up. So if you're going to have that extra breakdown, and that is usually when you would do it, is if you had a stratified random sample, because that's when you have the subgroup comparison. Then this sort of thing, if you have categorical data, that might be the kind of graph that you're going to end up with, because you can see that comparison in there. Let's see, then the Pareto chart, very, very similar to the bar graph, I guess, except that the bars are all touching each other. But the idea of the bars decrease as you go from left to right, that is, with the Pareto chart, that's a thing that you have to do. But the difference between this and a bar graph, they basically do the same thing, right? They serve the same function. There are just very slight differences there, like that the bars touch here and the bar graph they don't. Next, the pie chart. That's another option for categorical data. So This is another one where if you want to make this, you could. I would say a bar graph is more conventional than this, and it's actually probably a little better. I don't think of this as being a great option because, at least with the bar graph, all the bars are the same width. So the only thing that you're comparing is height when you look at the graph. So you only have to look at one dimension. Here, because it's using a circle, really the thing that your mind has to process is multi-dimensional, because it should be that the different areas are going to, correspond to like the differences in the count here versus the count here versus the count here. So that actually, like, it's extra work, I guess, in a way, like extra mental work, but it still does, like, it functions the right way. Although I think you're better off with the bar graph generally. The bar graph feels like it's more boring, but it's also more effective. So I guess that's the trade-off. Okay, so now that we've gone through the different options, then we've got what are graphs that are bad? All right, well, the one that's on the right side there is actually okay. The one that's on the left side, what's wrong with it? This. That it's not starting at 0. Because then the differences look way bigger than they actually are. Because over here, you go, okay, well, these vehicles aren't really that different in terms of size. Right, like you could say like a Camry's a little bit bigger, right? I would think a Corolla and a Civic would probably be essentially the same class of vehicle. But you think, all right, Camry's a little bit bigger, so the fuel efficiency should be a little bit lower. Okay, right? This bar is a little bit shorter than that one, right? Like that makes sense. But then you go over here, it's like, what is this? Right? Here it looks like the fuel efficiency of the Civic is like 5 times as good as a Camry. Right? It makes it look like a Camry has the fuel efficiency of like a tank or something when it's this low. So that's not true, right? But that's, with this picture, that's what it looks like, because the thing that you're going to notice right away is not going to be, oh, well, this is calibrated differently. It's going to be, this bar is way, way taller than this bar, right? It looks like you could fit 4 or 5 of this into this one pretty easily. And that's the problem, because that's not really what's going on. So the right side is really what's going on here, and that one starts at 0, right? There the height comparisons are actually correct. Here they're not, so that's the bad graphing technique, not starting at 0. This is another one, and this is supposed to be like a type of bar graph, except instead of using a bar, using a 3-dimensional shape. Using a 3-dimensional shape generally is not a great idea, because the data is not 3-dimensional, it's 1-dimensional, right? It's just comparing individual numbers. So using a 3-dimensional shape is actually going to cause trouble. So here's the thing that's trouble right here. It's that first bullet point. When a picture is stretched out to be twice as tall, but it's kept in proportion, it's also going to be twice as wide. So the new picture is 4 times the size of the original, right? Because if it's stretched twice in height and stretched twice in width, that's 2 times 2, right? So that's 4. And then here's one that's really cartoonish, because you look at this, and right, what this comes from clearly is some article that's trying to tell people to go to college, right? Because the $ boxes over here are so much bigger than the ones on the left side. But then you go, well, wait a minute. This number is a little bit less than 4 times this one. Or actually, they're about the same, I think. They end up being about, a little bit less than 4 times it. Okay, well, this box is not 1/4 the size of this one. You could fit way more than 4 of those boxes on the left inside of this thing. And that's the problem. Because this thing on the right should be about 4 times the size of this thing on the left, and that's not what's going on. So what's happening here is that the amount is about 4 times as large. But this is stretched 4 times in every dimension. So that box on the right, that's going to be, and I guess I can change this back to blue, it's about 4 times as wide, 4 times as tall, and 4 times as deep. So that's what I'm going to write in here. So it's about 4 times as wide, 4 times as tall, and 4 times as deep. And so what does that mean? 4 times 4 times 4, which is going to be about 64 times the size. And that's a problem because this number, the 74,602, it's not 64 times this, it's 4 times that. But that's not what the pictures look like because your mind is not going to view each dimension independently, right? Like when you look at that, you're going to see the whole thing, right? Like that's just the way that the human brain works. So, and generally that's a positive thing, right? You want to be able to see the whole thing that's there, not just individual pieces, right? You can process things faster that way. But here, when you see the whole thing, you're seeing the whole volume of this cube, and it's way too big. So that's the problem with 3-dimensional shapes. And that's why, like if you think like with a bar graph, you go, well, those bars are 2-dimensional, right? Because they have a height and they have a width. That's true, but all the widths are the same. So then the only thing that you can compare is the heights. And so that makes it a 1-dimensional comparison. So that's why the bar graph is better than this. All right, then there's the bar graph. You go, oh, yeah, right? There, this bar looks like it's about the 4 times the size of this bar. All right, that seems like that's what's supposed to be going on here. So the bar graph, good. Pictograph, bad, more or less. All right, then generally, things like histograms and bar charts and Pareto charts and pie charts, better for large data sets, even though you do lose information. Right? If all you had was the graph, you couldn't work backwards to essentially figure out what the original data set was. And you can do that with a dot plot or a stem and leaf plot, usually. Although if you have a large data set, then you have to start making adjustments and maybe you can't do it, or the data set's just so big that it just doesn't work. Which was like that one with the cab fares, where we had that stem and leaf plot that basically was going off the page, right? Like that doesn't work. You got to be able to get the graph on the page. So essentially where you would see these, and that's really what it comes down to, is you see these graphs here when you have large data sets, and you'd see these when you have small data sets.